So, an interrupt is what? What is an interrupt? If you're sitting in your room and your phone rings, that's an interrupt. If the phone doesn't have a working buzzer and you pick it up every 5 seconds, that's called polling. And if you can poll if your friend agrees to wait on the line for 5 minutes, then as long as you check the phone every 3 minutes, as long as he waits for 5 minutes, you're okay. And what that means is the mouse, if you can't get interrupt 12 working, just check it every 50 times a second, and that's good enough. Okay, well, let's. In the kernel, in the ints, kints, first you have to set up the two interrupt controllers. 8259, we learned this in school. I had to sneeze, hold on. Oh, okay. Anyway, there's one at port 20, and there's one at port A0. These are the traditional IBM PC interrupts. They start with it's 00 to, well, there's 16 interrupts starting with 0. Anyway, the processor has 256 vectors. That means what would be the analogy? I guess you have a doorbell, you have a telephone buzzer, you have a I don't know. Anyway, there's 16 different hardware interrupts. The others are can be software. What that means is, I don't think I want to teach. I just want to show you my operating system. I'm not going to teach you x86 architecture. So I set up my interrupts. I don't use the ACHI Advanced Interrupt Controller or whatever the hell that is. There's a newer mechanism for interrupts that's newer than the old school, but it's really complicated. So I don't. I did a demo in my demo lecture directory. If you go to demo lectures, do PCI interrupts. This attempts to, or this does PCI interrupts. I'm gonna hit a keyboard about 5 times. Okay, so instead of 16 interrupts, you have like A, B, C, and D, but it's pretty crazy. I don't even understand it, to be quite honest. I hit my keyboard 8 times. So this is the USB, but this is the ACE Advanced Interrupt Controller. So there's A, B, C, and D, but there's I don't even understand it. Anyway, I read through it enough to make this demo, and then I forgot. The problem is, even if it's too complicated figuring out which interrupt goes to what device. So I decided that was beyond the scope of TempleOS. It's actually clusterfucked on purpose by the CIA, but never mind. Anyway, so using the old interrupts, so we have to set up the 256 vectors. Only 16 are hardware. So, do you know what a software interrupt is? It's basically, well, I think I only use one software interrupt, and that's non-maskable. I don't remember. Software interrupts are slow, and I have no reason to use them. I don't change privilege levels, and I don't change stack. So the software interrupts are, I don't even think Linux likes to use them. They use syscall and stuff or whatever. So there's 16 hardware interrupts. Number 2 is now these two controllers, they're cascaded. What that means is the secondary chip is connected to one pin on the primary, and so interrupt 2, they have masters and slaves. Anyway, so in the let's go find the Intel data sheet. This is your best friend if you're making an operating system. What are we looking for? We are looking for I think number 3. Number 3A. Okay, we're looking for interrupts. So everybody at OS Dev is working on 32-bit operating systems. We need to look at the interrupt descriptor table for you get these. Basically, the first 4 times 256 bytes are in real mode. That's your interrupt vector table. In protected mode and long mode, you have a register that points to your table, so you can put it in other places. In real mode, it used to go at address 0, and that's why you don't see those used for other things. That's why things don't start at address 0 in real mode. So let's look at 64-bit mode. I don't think this... Basically, they're double the size, and there's 3 types of interrupt descriptor table entries. Handling in 64-bit mode. Okay. 64-bit mode. Okay. So it's this is 32 and another 32 and another 32 and another 32. So it's double the size. So the vector is kind of broken in pieces. Isn't that lovely? So you have the vector starting 0 to 15, 16 to 32, and then the rest of it. And then there's 3 types of interrupt descriptor table entries. There's a trap, there's a IRQ, and there's a I don't know. We only do the IRQs pretty much. I don't do software interrupts. I did a long time ago for I did some math operations. I had multiply and divide, I think, anyway, I had it, that was way back in 2005. Anyway, so these have to, normally you change from ring 3 to ring 0 to do system information. You know, all this stuff got really messed up. Now they don't even, most of this stuff is vestigial. I don't know what you want to call it. I think Linux uses syscalls, Linux and Windows. So this stuff is kind of like vestigial. You know how humans have tailbones? Anyway. So, you saw where the first 16 bits were the first 16 bits of the vector, and then the other 16, and then the other 32. So right here it's filling in an interrupt table vector. I do postfix typecasting, so I have a pointer and I'm typecasting it, and there's 3 different types. There's an IRQ, there's a trap, and there's a task gate. One of them turns off the interrupt flag, and one keeps it on. There's an IRQ, which is a hardware, and then I don't remember. There's one that keeps. Normally, you want to turn off interrupts until you finish and enable them. So that when the vector is called, it's normally called with interrupts off, and then you need to. Oh well, let's go look at a handler. So I forgot. I totally forgot. The first 32 interrupts are processor traps or so. I don't know what the terminology is. The first 32 interrupts are interrupt 13 is a protection fault. Isn't that what it is? There's a page fault. I should know. Anyway, there's divide by 0, which is number 0. And then there's an unmaskable. There's one that happens even if interrupts are turned off. And what I reserved that for, I got to thinking, what do I do if a core is crashed and a core has interrupts turned off? And so what I decided was I was going to use my unmaskable for rescuing a core that got turned off. I think that's what this is. I don't remember. So when you start getting into multi-core interrupts, they're kind of like software interrupts. You write a number to a you make a software interrupt by for a multi-core by multi-core interrupt. You write the interrupt number you want to be generated and stuff like that. Non-maskable, generate non-maskable. So these numbers here are you start getting into instead of using the interrupt pin, they start sending stuff over the bus. What do they call those? System management. I don't know if that's system management. I don't know. Anyway, the advanced interrupts are something I don't want to deal with. So once you have, let's go look at. So I use the timer interrupt, which is number 0. Where is my interrupt handler? The timer. I have a Jiffy count. This is called 1,000 times a second. It's interrupt 0, which means it's interrupt 32. It's hardware interrupt 0 out of 16, and it's mapped to vector 32, which is the first one after the ones used for the processor. It calls a routine that I have. Now I generate a multi-core interrupt on all the other cores every time I get it. Only core 0. I don't know. Is that true? Only core 0 gets interrupts. And I generate an interrupt. So I get 1,000 interrupts a second. and in my interrupt handler, I interrupt all the other cores 1,000 times a second. And I used to do preemption, and I would change tasks, but I don't do preemption anymore. And so this timer interrupt doesn't really do a whole lot. It used to be critical for preemption, but that I decided was beyond the scope. So as you can see, I've made some deliberate choices to keep it simple. And when I started seeing it getting cruddy, crappy, and clusterfucked, I said, this is beyond the scope of what I want. So I got rid of preemption. We don't use the advanced interrupts. They don't really provide anything better. I mean, a keyboard is a keyboard, right? It's not like you have a good keyboard handler and a bad keyboard handler. You know, a mouse, either a mouse works or it doesn't work. It's not like there's a good mouse, and you can't make the mouse better with USB handlers or something. So let's go look at, so interrupt 0 is the timer, 1 is the keyboard, 12 is the mouse, and are those the only ones we deal with? Now the keyboard and the mouse are PS2 legacy mode. I don't use USB mode, and they routed them into the same I/O ports, and so they get mixed up. Your keyboard and mouse data packets get mixed up unless you access them in the interrupt. Whenever you get a 1 interrupt, make sure to read all the keyboard packet bytes. When you get a 12 interrupt, make sure to read all the mouse bytes. And it turns out I've had computers where the BIOS enabled the keyboard, but it fucked up the mouse. And so I had to pull the mouse. When the BIOS starts, it sets these things up and gets them running. And I've had cases where the mouse interrupt didn't work, and fortunately I could pull. If the timer interrupt is interrupting 1,000 times a second, then all you do is it's like you pick up the telephone 1,000 times a second. As long as you can check it real fast, it's not really a problem. So I do. Am I missing one? I think I'm missing one. I don't remember. Anyway, so when I set up my keyboard, this is keyboard handler. This initializes the keyboard. It calls the routine to set the vector in the table, and then it unmasks it. There's keyboard is number 1, and what are we doing? 0, 1. That's a 2 because it's a bit value. You have 8 bits in the mask. A 1 is interrupt 0, so it reads the old value of the mask, and then it clears the bit, and then it pokes it sends it out. And so we're telling it IRQ keyboard. So IRQ keyboard is this is my actual handler. When the vector is triggered, it goes to this routine. Now I made my compiler smart enough to the old compilers used to Turbo C. Everyone used to write interrupt routines, and so the compiler had a keyword. Now whenever it sees the interrupt routine, the interrupt keyword, then that means the return is an IRET, and all the registers that normally get destroyed, it is careful to preserve those. So it preserves all these, and it uses an IRET. So my compiler is so kick-ass that it has an interrupt keyword for putting in front of interrupt keyword in front of the handler, and that's all you have to do. Here it's clearing the direction. When you do a move string constant, or there's anyway, that gets preserved. The interrupt pops the flags when it's done, and that returns them anyway. So what do we do in here? We acknowledge the interrupt to the, this is to the master. When we do interrupt 12, let's go ahead and look at the mouse. So the mouse, it has an interrupt handler, and this has to acknowledge both the master and the slave. You acknowledge the slave, and then you acknowledge the master. These are the two interrupt controllers that each do 8. They're cascaded, and we read a packet. I check if we've had a timeout error and reset it. Sometimes I think a packet is like 3 bytes or something, and 4 bytes. If something got screwed up, you want to flush the old couple bytes. If it's been too long, you want, I don't know. Some of this stuff I'm not actually sure is necessary, but I do it. As a matter of fact, when you're using VMware, when you're using VMware, once in a while, you can, I'm pretty sure you can miss a byte, and then you get out of sync. If you're expecting 3 byte packets and you get out of sync, that's bad. So I get the timestamp. The timestamp is the fastest timer you can read. What I mean is, well, HPET is just as fast. I'm not talking about frequency. I'm talking about how fast you can read it. Well, HPET is pretty fast, but I've had things that didn't have an high performant event timer. The problem with the timestamp count is this is like 3 gigahertz, but the processor gets throttled and stuff like that, so it's actually anyway. So I use a FIFO for my packets. They're so tiny, I really didn't need that, but I went ahead and did it. I think it's 3 bytes. This is checking if we have too many, and what is it doing? Oh, it's transferring them from a there's 2 FIFOs, FIFO 0 and FIFO 2. I think that's just, why did I do that? If it gets a well-formed packet, it transfers it. And as a matter of fact, I might do that in the timer. I have a window manager task. I have a couple of executives. The Atom task doesn't really. The Atom task doesn't run all the time. The Seth tasks do run. The window manager runs. The Atom task, I think, stays asleep until he actually gets a request. the window manager runs the window manager runs 50 times a second, I think. No, 30 times a second. We refresh the screen 30 times a second. I don't even remember. So I have a couple of maintenance. I think we process the mouse packets and keyboard packets. I think they call it pumping the packets. So he has the window manager has a sleep, window manager sleep. So this is kind of like the idle, I don't know what you want to call it. When I can go ahead and explain. When you grab a window and move it, what has happened is the window manager has detected the left button down on the title bar, and that enters like a state machine. When it gets the left button down, if the old left button was down and the new left button is up, okay, what we, in that case, we want old left button is, we want old left button up, new left button down. Then some of these things stay in a loop, and as they're looping, they're calling the sleep, and that's the way the window manager manages. So you get these loops where it's calling the sleep, waiting for the button to be released. And so the sleep I think I screwed it. Anyway, the sleep pumps it pumps the messages, so it takes them out of the FIFO and processes them and it gives them to the windows that are the tasks in question. So how about that? Let's call it a day.